Yeah. All right, so yesterday, guys, I think we finished talking about finding the distance on a number line between 2 points. Okay, so I'm just going to put on here a series of points. Let's go 0, let's go 7, 11, 38, 50, 200. Okay, so the reason I do this is because I want to make sure that we understand the concept that is always going to get us the correct distance between 2 points, okay? So if I gave you a number line that was structured to where the intervals were the same and that we never skipped over any values, maybe I just gave you the integers, so 0, 1, 2, 3, 4, 5, 6, all the way to infinity, and then their opposites. It would be pretty easy to count over how many units are between two endpoints, right? Okay. That's not the best strategy. One, because the end-of-course exam is not going to ask you to do that. The end-of-course exam is going to give you something like this, where they give you a number line and they say, find the distance between B and G. Okay? So say find length BG. And what we have to do is understand that on what we call it the one-dimensional number line, meaning it only moves left to right. Okay? If you think about your X and Y axes, those are two-dimensional number lines. Okay? Because you got one going left and right, one going up and down, right? Okay? This is just a one-dimensional number line. So the way we approach doing this, if I call this coordinate here lowercase b, and I call this one lowercase g, we talked yesterday that we're going to take g minus b and then take the absolute value of that difference. Remember doing that yesterday? Just subtracting them and then taking their absolute value. It doesn't matter, because the fact that we're doing absolute value, it does not matter the order that you subtract them. So if you want to go b minus g or g minus b, doesn't matter. But if we go 11 minus negative 34, what's minus and negative turn into? Turns into addition, right? So I got 11 plus 34, so it gives me what, 45? So the absolute value of 45, which just turns into 45, which then is different than counting 1, 2, 3, 4, 5 spots, right? That make sense? Okay. Every year I give a question like this on the first chapter test, first chapter quiz, and inevitably, thank you, inevitably somebody will say the answer is 5, because all they want to do is count. Okay. But we have to use the formula. Last class somebody said this. They said, well, just take the absolute value of your two numbers and then add those together. So they said, if I wanted to find, let's just do one of these real quick. Let's go, we can do B to G. They said we should be able to do this. Absolute value of B, and then plus the absolute value of G. If I do that, what's the absolute value of B? So negative 34, plus in the absolute value of G, which is 11. What's the absolute value of 34? Negative 34. 34. What's the absolute value of 11? 11. Does that still give me 45? So their argument was, well, Mr. Fay, you told me that the blue equation was what we needed to use. I prefer to use the yellow one. And I told them, okay, if you do that, you're going to miss a third of the questions. Okay? Because if we look at that yellow one, though it works for this situation, let's talk about when maybe they're both, let's go C to D. And it might be more than a third of the questions that they're going to miss. If I go C to D and I use this yellow rule, I'm taking the absolute value of C, which would be negative 18, absolute value of negative 18, plus the absolute value of negative 11. So it'd give me 18 plus 11, and I would be saying that there's 29 units between those 2 points. Is there 29 units between negative 18 and negative 11? I mean, that's one we could probably do in our head and say there should be 7, right? Okay? So my hope is that you see that even though there is an expression or a formula, the absolute value of B plus the absolute value of G, that will work occasionally, and it works if both one number is positive and one number is negative. It is when it works. Okay? If they're both positive or if they're both negative, you're going to run into an issue. Okay? So I think you're going to miss 2/3 of the questions if you go by that route. Okay? So we need an equation that will always work, and the equation that will always work, so we're looking for this 29 to end up being, what do we say, 7? So if I do CD is equal to the absolute value of negative 11 minus negative 18, that's going to give me the absolute value of negative 11 plus 18. That's the absolute value of 7, which is then just 7, right? Does that make sense? Okay? So we have to be able to use that formula, all right? Counting is a technique that you're going to hear me over and over throughout the year because everyone wants to do it because it's the fast way. Okay, so when I ask you to do, we'll do some slope stuff in this course. We'll do a lot of maybe real intricate techniques with formulas that people say, well, I can just, on this example, I can just count up and over, or I can just count my X distance, or just count my Y distance and get the answer that he's looking for, which on that example is fine because the numbers I gave you it works with, but then you never learn the right approach or the formula approach. And when I take those convenient integer numbers away from you and give you fractions, or give you decimals, or give you numbers like pi and e and radical 2, or your rational numbers, now you have no basis for doing that problem. Does that make sense? Okay, so we want to learn the formulas and not necessarily the shortcuts. So you guys have used this stuff before. You've seen, we kind of ended class yesterday with an argument that I think we're talking to Landon about driving down 75. So here's my crude Ohio. Okay, so let's say that we're here in Toledo. Then we've got Lima down here, and then down here we got Cincinnati, right? If I'm in Toledo, okay, just driving down 75, on the side of the road, I'm going to see a mile marker. That mile marker might say like mile 12. Okay, it might be 12 miles from the border. Does that make sense? I get down here to Cincinnati, and that might say mile 188. Okay? If I started at mile marker 12, and I go to mile marker 188, if I take the absolute value of 12 minus 188, or the absolute value of 188 minus 12, okay, and I get, what's that going to give me, 176? No, yeah, 176. Does it tell me that I've traveled 176 miles on I-75? Does that make sense to everybody? Okay. And if I can do that maybe in 2 hours, I can take 176 miles and divide it by 2 hours, and now I have an average rate of travel. Does that make sense to everybody? Okay, so that's an application, a real life application of using these endpoint ideas. Okay, I don't know. Did I talk to you guys about using a tape measure? Okay, if I'm going to measure something, let's say I want to measure the smart board here. Most of you are going to take a tape measure, and it's got that little hook on it, and you're going to grab the side, see here, find something I can grab onto. Well, you get the idea, okay? So I'm going to grab the side, and that's where that hook is going to be 0, right? Does that make sense on my number line? Let's do my desk. So where my hook is 0. Come over to my desk, and right now, the other edge of my desk goes through 60. So my desk is 60 inches long, right? Okay. Well, what if, I told my last class that my daughter likes to play with these. This is my only I got like 12 tape measures. It's the only one that works. Because she breaks the ends of them. She thinks like this is fun, like to see how high she can get it. And then it falls, and she steps on it and breaks them. So none of my tape measures have like this end here working, or it's all crinkled up and bent. But if I put it on 6 on that end point, and then come down here to see this other one, you can see that it goes through 66. Does that make sense? So how long is my desk? If I started at 6 and it ends at 66, how long is my desk? 60 inches. So with a tape measure, we don't have to start at 0, right? Any ruler, any yardstick that you use, you don't need 0 to be your starting point, okay? If you're going to use something else other than 0, you need to make note of it, okay? And then find out the other endpoint and then just subtract them. Why do we use 0? Is 60 minus 0 a lot easier than 66 minus 6? Yeah, okay? That's why we like to use 0, but you don't have to, okay? So those are maybe 2 applications of that distance formula that is a very generic, basic formula for geometric concepts that we then convert over to real life and use in real life, okay? So I think, and we talked about this in the last class as well, I think there's some things in this course, guys, that are kind of boring, okay? If we can talk about like how that math transfers over, converts over to real life, and maybe makes it a little bit more applicable, and make more sense on why we're talking about it. And one of those places that we can do that is in construction and building things. Because we're usually measuring things and trying to make things, making angles, right angles, and making sure distances are consistent. And we see a lot of that geometry go over into building, okay? Which is nice for us because probably at some point we're all going to either own a home or rent a home or whatever. We might like to do some remodeling. And if you don't know anything about geometry, you're going to have to either remodel and it look like crap, or remodel and have somebody do it for you and probably pay 2, 3, 4 times as much as what it would have cost you to do it yourself, okay? So there's a lot of things that you guys can maybe take from this class that maybe 10, 15 years from now you'll come into contact with and say, okay, well, that makes sense. I've done this before because I talked about it in 9th grade, 10th grade geometry. And you can maybe save yourself a little bit of money. The next thing I want to talk about today, guys, is this is the main topic today. It's called the segment addition postulate. And I told the last class if we're going to go through the rest of the textbook and kind of catalog take each topic and kind of put a tally next to it, how many times that topic shows up through the rest of the book, this one would be the most, okay? This one is used in almost every chapter from here on out, okay? So it's very, very important for us to learn this and to learn it the best we can as quick as we can, okay? It's a postulate, so it's something that we cannot prove, but it kind of makes sense. Let's go back to the idea of traveling here. So let's say we've got Ohio again, and then I've got, I don't know what Michigan looks like, but I got Michigan above it. Okay, I don't know where it goes over here. Let's say here I'm at Lima right there. Let's say it takes me 115 miles to get to the Ohio border. Okay? And once I then get to the Ohio border, I stop, maybe get some gas, whatever, and then I want to travel straight up 75 to get to Detroit, and maybe that's another, 65 miles. How many miles did I travel from Lima to Detroit? 180. Is that pretty easy? That's the segment addition postulate. That's all that's saying. If you know the two smaller individual distances traveled and you sum them together, you then know what your entire route was, or your entire trip. Okay? So what we do in mathematics is say, okay, that's not, obviously using that example is not enough to provide a rule. So what we do is we try to condense and make a statement that is as concise as possible, and this is the type of statement that comes out. Okay? Instead of using Lima, Toledo, and Detroit, we say we have some just random points A, B, and C. Okay? Which then could stand in for any city, any three cities that we wanted to talk about. Okay? We're going to add the fact that they're collinear here. Okay? So the idea is that I-75 from Lima to Detroit does not bend at all. Okay? What it says is the 3 points are collinear, and B is between A and C. So all the rules that we get this year are going to be written this way, where they give you an if statement. Okay? So that statement that I highlighted, I'm going to interpret that as if this is occurring in front of me, if this is the picture, if this is the scenario or situation that I'm being presented with, I can guarantee that that is happening. Okay? Then I can make the conclusion, I can argue that AB plus BC equals AC. Does that kind of make sense? Okay? Without that yellow stuff happening in the way that it's defined in that yellow statement, there's no way for me to argue AB plus BC equals AC. Okay? And we'll go through this example here, and then we'll tackle that statement a little bit more and address it in more detail. But what the segment addition postulate says, if you have 3 points that are collinear, okay? So let's look at, I made that too big. All right, so if we look at that segment right there, it says EG is 59. What is EF and FG? If I look at my picture, can we argue that E, F, and G, kind of like A, B, and C up here were, are they collinear? Okay? In this case, F is between E and G instead of B being between A and C. Here it said then AB, that distance there, plus BC, which is that distance there, should give me the whole. So down here, using our specific values of E and F, or points E and F, we should be able to say EF, add to it FG, that should give me then that total distance, E to G. That kind of make sense to everybody? Okay. You guys remember using substitution last year? Okay, so if I have an expression like x plus y, and I tell you that x is 5 and y is 10, you can substitute those values and get a result of 15, right? We're going to do the same thing here. I'm telling you in the picture that EF is 8x minus 14. So I'm going to replace that with 8x minus 14. FG, they're saying, is 4x plus 1. So that plus sign right there needs to be carried down. But FG is 4x plus 1. And now what do they say EG is? EG is provided over here in the direction. When you guys kind of look back to, and this is what I hate about algebra, and then we take geometry, there's no way around this. If you go back to all your algebra, like directions, usually your directions in algebra are either evaluate, simplify, solve for x, that kind of thing, right? Very simplistic directions. Every time we see a geometry question, the directions are going to be different. And most of the time they provide you pertinent information inside the directions. So this one would say, in the direction, if EG equals 59, find what EF and FG are. Those are the directions. Okay? So if I don't pay attention, because a lot of people don't like to read the directions, we might write down 8x minus 14 plus 4x plus 1, and have no clue what to do because we haven't read the directions. Does that make sense? Okay? So you're always going to find good information in your directions. So now we got an equation. Can we solve that? How many x's do we have? Careful. There's two. Visually, there's two, right? But doesn't that mean there's 8 of these x's? And there's 4 of those ones? So we got 12 total. So 12 x's minus 13 when I add the negative 14 into the 1 equals 59. What do I do next? Plus 13. So I get 12x, 72. Good. Okay. Now, as we do, and I'm just telling you this stuff because obviously it's the first time we've done algebra together. We passed algebra, right? Okay. Now, chances are you probably got a C or a B or an A in that class. That's what put you here. If I take any liberties in regards to our algebra, like I skip a step, I skip 2 steps, or I do some stuff in my head, or maybe I just say, okay, we're going to stop there and I'll let you guys solve it on your own, okay? Because maybe we want to target the geometry a little bit more in class than the algebra. If there's every time with the algebra that you get confused because of something that I'm doing, let me know, and I can slow down, I can repeat, I can do it a different way, that kind of thing, okay? But there might be times where we get down to like 12x minus 13 equals 59 in a problem. I say, okay, I'll let you guys finish that on your own, but we've seen the geometry. Does that make sense? The geometry, guys, was this right here. Writing that was the geometry. Taking the picture and writing that equation. Once we got the equation, then it's all algebra 1. Okay? Was that? Mm-hmm. That's the only geometry part of that question. And that's what we're going to find out in a lot of the stuff that we do. There's a very quick, very simple geometry relationship, and that builds an equation, and now you got to rely on your algebra to solve that equation. Okay? But now here's the thing. Last year, when you got X to be an answer, probably 99% of the time you were done. You just circled it, moved on to the next question, right? If I do that here, I'm wrong. If I'm in Math Excel and it's multiple choice, A, B, C, and D, and D is 6, and I got 6 here, and I go click D, and go to the next question, it's going to tell me I'm wrong because I didn't answer the question being asked. What's the question being asked? Right, we've just found X, right? EF and FG are these 2 distances that I've got to take this 6 and substitute back in. So that's going to give me 8. What's 8 times 6? 48 minus 14. Should be 34. When I plug in 6 here, get 24 plus my 1, 25. Okay. Now, I don't know where that 3 went. I should be able to check myself. And all the questions we do throughout the entire year, especially the algebra ones, you should always be able to quickly check yourself. If I take 34 and 25 and add those together, what do I end up with? Yeah, I get back to the 59, a number that I wasn't trying to get to, but by adding those things together, it produces a 59, a number that was given to me earlier in the problem, right? Okay? And if I can replicate that number without trying to, okay, I can be guaranteed then that those 2 numbers, 34 and 25, are correct. Okay? Now, I want to change something a little bit. I'll ask this question to you on a test or quiz. I'm going to say, let's go, if A, B, and C are collinear, then AB plus BC equals AC. I'm going to ask you, is that true or is that false? What do we think?
True.
True? Who says true? Show me a hand. Show. Okay. So if that's true, there should be no situation that I can come up with that would contradict it, right? That would make it false. Okay? Look at that statement right there. A, B, and C are collinear, then AB plus BC equals AC. Let's go back a slide. Here it says, if 3 points A, B, and C, so very similar to what we had, are collinear, still very similar to what we had, and B is between A and C. Did I incorporate that statement, that B is between A and C, in that argument there? No. Okay? All I said were A, B, and C are collinear, right? Now that could be A, then B, and then C. But it could be B, then A, then C. Or it could be C, A, and then B. But here's the thing. Because I don't tell you their order, A could be there, C could be there, B could be there. Does that make sense? I abide by this. If A, B, and C are collinear, then is this thing here true? Well, A to B would be that distance there. B to C would be that distance there. So if I add the yellow distance and the blue distance, does that give me that distance there? No. Okay? So you see how removing a phrase out of a statement, out of a rule, can completely change the way I interpret it, and it might not always make that rule or the conclusion of that rule true. So this would actually be false. Okay? Let's do this. I'll put that phrase back in. I'll put B between A and C. So let's say if A, B, and C are 3 points, and B is between A and C, then AB plus BC equals AC. And the question again, is that true or is that false? I put that phrase back in, right? Anybody recognize what I left out though? I didn't put collinear in. Okay? So A, B, and C, 3 points. B is between A and C. Now this is kind of maybe a weird way to think about this. I don't know if logically this makes a whole lot of sense, but if that's A and that's C, maybe there's a debate on whether if I call that B, if it's between A and C, but I think most people would argue that it is between A and C in some manner. Would you argue with that or agree with that? Okay? Now here's my question. If that's happening, so this phrase right here, because I eliminated the word collinear, that phrase is allowing this red picture to happen. Okay? So now the question is, does this then end up being true? If I travel from A to B, and then follow that up by traveling from B to C, is that going to be the same distance as traveling from A to C?
No.
No. Going the blue distance followed by the green distance is going to be longer, isn't it? Okay. What's the shortest distance is always between? Yeah, it's 2 points, right? The shortest distance between 2 points is always a straight line. I guess that's the phrase I was looking for. Shortest distance between 2 points is always a straight line. If I'm going from A to C through B, I'm not using that shortest distance, right? Okay? So this, again, would be false. So excluding key phrases will incorporate or allow other pictures or other kind of setups for the things that we see in the if statement to occur, And if that happens, we have to think about those and see if they violate the then part, the AB plus BC equals AC statement. Okay? That is one of the things that is very, very, very difficult in this class to think about. And really every math class beyond this that you have to prove things. It is hard to visualize all of the different scenarios that could happen. Okay? And just by practice and seeing them over and over and again, so the next time we see a postulate like that gives us a rule, we'll mess with it. We'll take words out, we'll add words in, and see then how does that change the picture that could be created, and see how that then changes the overall conclusion. This is the same type of problem, guys. I should write here A, B, and C are collinear. Okay, B is between A and C, so I'm meeting that criteria that was being stated in the postulate. And then I give this picture because you will be asked from time to time to draw your own picture, to organize your information without the aid of the author of the textbook or something like that. So if I've got A, B, and C here being collinear, B is between A and C. So that means that's got to be A, and that's got to be C, right? Now it says B is in between. So B can be anywhere. It doesn't matter, okay? It doesn't say it's closer to A. It doesn't say it's closer to C. So you can put it anywhere you want to, okay? So I'm just going to put it right there. We'll see at the end if that was a good placement for it or not, based on our conclusions. All right, so it's saying that AB is X, right? So if I look at AB, and then look at BC, that should give me kind of that total there, right? I like to color code things. I know you guys can't necessarily do that with your pencils and pens, but I think it allows me to see that I can write this equation, AB plus BC is equal to AC. And they told us that AB was X and BC was X plus 6. So I replace AB with what it's equal to, X. Do the same thing with BC. And what was AC? 24. All right, so now we get down to an equation that hopefully we can solve, right? Okay. I'll let you solve it on your own, but we do get X to be 9 here. Okay. So if X is 9, I put 9 there when I substitute, and that's going to give me 15, right? Does 9 plus 15 get me back to that 24? My thought is, guys, that once you can do 2, 3 of those, they're all the same. Okay? And there will be times maybe that they word it so you've got like A to B, and you got B to C, and you got C to D. Well, the idea is that AB plus BC plus CD, these 3 individual segments, will add to AD. Does that make sense? If we've got 4 collinear points or we've got 34 collinear points, we should be able to add up the individual segments that are created by those points to get the total, to get the overall. Okay. The next couple slides talk about some vocabulary. Okay, and this is one of the most important vocabularies in the entire textbook. Okay, and you guys heard of congruent before, right? Okay. Now, I don't know that you've been taught, because when I was in high school, my teacher never taught me what congruent really meant. Okay, it was just something that we kind of associated with equality, but we moved on. Okay, it's very important that we understand there's a difference between congruency and equality. If there wasn't a difference, there would not be 2 vocabulary words, right? Okay, so congruency is the idea that 2 shapes are the same type of shape and that they have the same size. Okay, so have the same features, same characteristics that dictate their size. So what we're saying here is that if 2 shapes are going to be congruent, they both need to be segments, or they both need to be triangles, or they both need to be angles. So an angle will never be congruent to a segment. Does that make sense? They're not the same shape. An angle will never be congruent to a circle. They're not the same shape. Okay? So we need that criteria first. The next thing we need is that their sizes have to be the same. Now, as we talk about different shapes, there will be different things that dictate their size. For instance, a segment, the only thing that dictates the size of a segment is its length, right? Think about a circle. The only thing that dictates a circle's size, does anybody know what is the only measurement of a circle that we use to dictate its size? Anybody know? I'd accept two answers here. They're related to one another. When I use a circle formula, like area or circumference, what's the only thing that you pull off the circle that you use? The radius. Okay, 2 pi r or pi r squared, right? Okay, pi is a number. Okay, so r is the only thing, radius. So a radius dictates the size of a circle. Squares, the only thing that dictates the size of a square is the side length. What about a rectangle? What dictates the size of a rectangle? Does just the length dictate it? Say again? Okay, so which sides? How many of them? 2, right? The length and then the width, right? Does that make sense? Those are the two values that dictate the size of a rectangle. So when I want to talk about rectangles being congruent, first I got to make sure that they're both rectangles, and then I got to compare the lengths of both of them and then the widths of both of them. Okay? If I want to talk about triangles being congruent, I've got to compare all 3 angles and all 3 sides. So I got 6 things in triangles that I can compare to make sure the shapes are congruent. So the more we start talking about individual types of shapes like segments and triangles and angles and that kind of stuff, we'll revisit this. But in order to be congruent, same size, same shape. Segments are really easy to deal with, okay? This is the definition of congruent segment, segments that have equal lengths. If I read that, it incorporates the idea of same shape, because it says segments, right? It's talking about 2 segments, 3 segments, 4 segments, they're the same shape. And they have the same size. Their length is what the size is predicated on. The way I want you guys to think about congruency is the idea that I should be able to... So congruency is almost kind of a visual thing. If I have that red segment in my left hand and I have this purple segment in my right hand, I should be able to take them and overlap them and they match 100%. Does that make sense? That's what congruence, that's what we want to visualize congruency as. Okay? In order to do that, obviously they have to be the same shape, right? And they have to be the same length. When we talk about equality, things that are equal, only numbers can equal numbers. Okay? So like 8 up there, 8 is equal to 8. Okay? A number equal to a number. We can't say a segment is equal to a segment. Does that make sense? A shape is not equal to a shape. A shape is congruent to a shape. Okay? So congruency is a little bit more than just equality. Does that make sense? Okay? And congruency incorporates sizes that are equal. Okay? But then it also incorporates that the shapes are the same type of shape. Okay? So there is a difference between them. And I want us to kind of recognize that. If I want to talk about congruency by hand, I don't want to write out in words that 2 distances are equal or 2 lengths are equal. So the shorthand of it, if I want to say segment AM and segment TZ have the same length, I write that. That says length AM or distance AM is equal to length or distance TZ. If I want to write that they're congruent, if I want to tell everybody that's reading my work that these 2 shapes are indeed the same type of shape and they overlap each other, they lay on top of each other perfectly, I'm going to say that shape AM, which is a segment, so I use the segment symbol. I'm going to write congruent. You guys have seen this symbol before? And then TZ. This one up here says a number is equal to a number. This one down here says a shape will lay on top of another shape. They will match up 100%. Another congruency symbol that maybe you probably haven't seen it, but a lot of your like Windows or stuff like that, when you get on Word and start typing congruency things, that might be an option for congruency. So it's just 3 equal slashes. Okay? It's like an equal sign with another slash on top of it. I'll jump back and forth between the usage of both those. The top one is what you see most of the time in like a high school class. That bottom one is more kind of the next level. You see that, start seeing that in calculus a little bit. I want to talk, at least get through the midpoint definition. And we kind of talked about this the other day. We took the shoestring or the piece of rope I had and we put the endpoints together and found the middle point, right? Okay? The midpoint is a point on a segment that divides the segment into 2 congruent parts. All right, so if I say if M is the midpoint of AB, segment AB, then what that produces is AM congruent to MB. And I'll give you a picture for that. MB. Have you guys in your other classes, like, I don't know, last time we talked about geometry, it would have been 7th or 8th grade. Did you guys use those symbols inside those line segments to show congruency? Just a little hash mark? Okay. That notation allows me to visually look at a picture and determine what things are congruent and what things are not congruent, instead of having to look back at the text for that particular problem. Okay. But that's what we're saying when we have a midpoint. It's producing 2 segments that are congruent, meaning that AM is going to fall. If I chopped AM off and slid it over, it's going to land exactly on top of MB. So what's that mean about their lengths? If AM and MB are the same shape, they're congruent, so they're the same shape and same size, right? Their lengths have to be what to one another? The lengths are the size, so they got to be the same, right? They got to be equal. So I want to get to a question, and this will be the last thing we do. I know we're getting close. This question looks very similar to the other segment addition questions we've done, right? And I'm going to approach it incorrectly at first, okay, to prove a point. This is what a lot of people will do. We'll see 5 or 6 segment addition questions in our homework, and then this one will pop up. And we won't read the directions. We'll just say A plus 11 plus 2A minus 5, and we'll put our equal sign, and then we start searching, and we can't find what's supposed to be equal to. Okay, because they don't tell me what X, Y is, right? Always read your directions. Your directions tell you W is a what? Midpoint. So that distance there and that distance there, those 2 distances are the same, correct? So what's it telling? And this is the distance for X to W. That's the distance for W to Y. If they're the same, what is the algebra that I use to show them the same? What am I going to put between them? Equal sign, right? Now do I have an equation that I can solve? Yeah, solve that. You should get, subtract A from both sides, add 5 to both sides, you get A to be 16. Okay, so I'll let you do that math a little bit on your own. But now let's validate it. Let's see if that is actually true. If A is 16, I plug that back in here. What's 11 plus 16? 27. Plug in here, I get 32 minus 5, which is 27. When I have a midpoint, doesn't that mean the distances are the same? And that's what we're proving with 27, 27. Okay? So you'll see a handful of questions like that. I do have a math Excel assignment open for you. It'll be due tomorrow. Okay? It should not tax you in regards to time. It should not be something that takes you over. I'd say if it takes you more than a half hour, we've got issues. Okay? We talk about all those tomorrow, or as many as we need to tomorrow. For the first couple weeks, guys, it's going to be hot here, and there's nothing I can do about it. Hard to stay awake. I know that. Bring bottled water. Keep yourself hydrated. Be easier to stay awake. If you guys stand up, okay? When you guys are sitting in your seats like this, all your blood pools in your calves, so it's not getting to your heart. It's not keeping you awake. Does that make sense? So if you do, like, heel raises with your feet, that will do a lot to stimulate you and keep you awake, okay? So those are little tips and tricks that you can use as we move on. Once it cools down, it'll be a lot better, okay? But for the next week or so, it's going to be hot.